Welcome. I think the fusion inequality has a simple proof using the spectral monotonicity, which we have proven. So we have an inequality between the eigenvalues, a spectral inequality between the eigenvalues of a subcomplex of a simplicial complex. So K is a closed set, which means it's a subcomplex, and U is the complementary open set, and both have a Betty vector attached. And we have these inequalities, and then we can just conclude using the Fisher argument to also see that when we add things up, that we have here the inequality with a 2. It's not true without the 2 in general. I tried to enforce this using the Witih deformation, and I think it's true when you do a Witih deformation that you can actually get the 2 away, but in suitable coordinates. But this is enough for a proof. If we have that, then the number of eigenvalues, 0 eigenvalues, is larger or equal in the disjoint part than in the fused part, and that's all we need to see. So I'm writing this down now and see whether this really holds up, but I don't think that there is any difficulty. I think I've been very close to that already, but kind of dismissed it because of not looking at it in the right way. That's about the fusion inequality. Now, if we have that, we can look at various questions. We can, for example, look, when do we have equality? And so here we have an example where we have equality, this manifold case, orientable manifold, closed and an open part. You fuse them together, and then it just adds up. So that's a nice case. That's how I started that whole thing. And I first thought that it's always an equality, and then I looked at the projective plane. In the projective plane, it's not true. There is no second Betty number. So this is a kind of a nice example where we have a minimum, but then we can also look where do we have a maximum. And I looked at some examples this week. So first of all, we can look at the case when we take 1 point away, when K is 1 point. In this case, you can actually conclude that the B1 has just increased by 1. That's the only possibility which we can have. And in general, if you take now more points away, then the first Betty vector gets just increased always by 1. This is very interesting because now we have 1 forms created. And we are looking at that. We have 1 form. In the 2-dimensional case, this is kind of clear because we can have kind of created new loops. But this is in general. We can, for example, take a 3 manifold. We take n points away, and then we create this additional cohomology, which is very, very strange, and I don't understand yet how they look like. So one can look at these harmonic forms and see how they actually behave. Another interesting case is kind of the circle manifold case, and especially something which is interesting. So if you have a manifold G and you have a submanifold K, that's kind of a very special situation. But in this case, what happens is, if you actually look at that, I was running, of course, experiments to see what happens when does it become maximal, just by adding and removing randomly some simplices, and see whenever it increases, when the number of this excess increases, then I'm going with that. So it's kind of a simulated annealing. What I have seen always in the manifold case, that just the maximal case is if all the maximal simplices together. It's not a disjoint set of open sets, but it's an open set. It's a union of open sets, right? This is a topology. We have open set. The maximal simplices are open sets, and we have a union of open sets, which is just disregarding every 1-dimensional and 2-dimensional simplex. By the way, this whole thing is related to a science fiction novel of Greg Egan, which it's a strange novel, and but very, very mathematical. And you see the beginning here already mentions a graph. And so the story is that there's a universe and there are rules. There is a small part which I imagine to be K, where a different rule works, and this expands this new universe. Within the universe eats up the other universe, and these creatures in that universe which are running away from that expanding bubble. The name comes from Schild's ladder, comes from this numerical method to compute the parallel transport in a Riemannian manifold. So if you have a Riemannian manifold and you go along the path, Then you can do parallel transport. You can see how the vectors get transported. And this Schild's algorithm is a numerical algorithm which is better than a naive algorithm to come. And that's important in relativity. So he was at UT Austin and founded the relativity center. This novel here is deals with a graph, and the edges have no length nor shape. The nodes have no position. So that's kind of the philosophy, that you are not looking at any geometric realization of this space. But in this case, we are kind of just looking at the mathematical problem of having a subcomplex of a simplicial complex, and we look at the subcomplex where this excess cohomology is maximal. Maybe there are some interesting geometric features in that case, and I tried to see this in examples. So in the case of manifolds, it seems to be quite clear what happens. That's it.